Welcome GeoTrig. This is 6.4, Graphs of Polar Equations. The essential question is, what are some features of graphs of polar equations? Let's begin. So when we graph polar equations, we want to use a graph that has polar grids. So basically instead of x and y, just do I guess it's kind of like an x-axis, but it's kind of your r-axis now, and then put your degrees in the outside. In this case, we'll keep it in radians just to be consistent here. Now, I think this lesson is kind of fun. You're just basically figuring out what the shape is based off an equation. So let's try these, and let's start with the circles because we've done those before, and those are probably the simplest. So the equations for the graphs look like r equals a cosine of theta, and r equals a times sine of theta, where a is some positive coefficient. So when you have that, you'll have a circle, and so when you have cosine, it's going to be pushed, it's going to be basically on your x-axis, and the diameter of the circle is going to be a, and it's going to, one edge is going to be at the origin. And when it's a sine, it's going to look like this. So basically going on the y-axis, where again, a is your diameter. So let's actually try to look at an example here. So if I want to graph the equation r equals 4 times sine of theta, well, in that case, my a is going to equal 4. And so your circle is going to start on the origin, and then since it's positive 4, it's the diameter here is going to be 4. And we can, if we want to, we can always plot a few points to verify this. So you can easily plot in different, instead of doing xy chart, we do a theta r chart. So you're plotting in values for theta. So do your easy ones from the unit circle. So 0. If you have 0 for theta, sine of 0, that's your y values, it's going to be 0. So 4 times 0 would be 0 for r, which makes sense. That's going to be at the origin. Let's say another one that's easy. Let's go pi over 2. Now sine of pi over 2 is going to be 1, so it's going to be 4 times 1, which will be 4. So at pi over 2, which is right here, your r is going to equal 4. And that makes sense because that's that point right there. And you could do other ones. What others would you know? If you tried to graph, let's say, 2 pi over 3, so 2 pi over 3, you know your sine of 2 pi over 3 is going to be, let's see, that would be your y value. So that's going to be square root of 3 over 2. So it's 4 times square root of 3 over 2, which reduces to 2 square root of 3. And if you plug that into a calculator, 2 times square root of 3, you're going to get approximately 3.46. And right here, this value, if you count your r going out 1, 2, 3, this value right here, that's about 3.46. So that's what's going on. Yeah, if you want to plot these, you can take a few the thetas that you actually can figure out. You might need a calculator to calculate some of that, and you can actually graph these shapes. So let's look at a few different things. Symmetry. So these plots can be symmetric. I'm not going to emphasize this much, but there's 3 different ways. There's symmetry with the polar axis, symmetry with respect to the line theta equals pi over 2, and symmetry with respect to the origin. Here's an example of this. I don't want to do much. I want to graph. So let's go on to the next graph. Lymassans. So these are what these are called, Lymassans. And the equations are of these forms up here. Your r equals some constant a plus times b sine of theta, or cosine of theta, or minus b sine and cosine of theta, where a and b are positive. So these different shapes here, they all kind of look the same, but sometimes this one's curved in more than the others. To tell which kind you're going to look at the ratio of a divided by b. So if a divided by b is less than 1, it's going to form the loop inside. If it's equals 1, you're going to get this heart shape. There's no loop. If it's between 1 and 2, you get this dimple where it's just kind of floating between there. It's almost a circle with a dimple. And then if it's greater than 2, you're not going to have a dimple at all. It's going to look pretty flat right there and still going in here. So let's do an example. I want to graph r equals 1 plus cosine of theta. Now, my a in this case is going to be 1, and my b in this case is going to be 1. So your ratio of a divided by b is going to equal 1. And that's going to form a heart shape here. So I know I'm going to expect a heart shape. Now, if I want to graph this, notice the line goes out this way forever. We can plot a few points. Like maybe we want to know, well, how far out is this? Now, I can make my table again, because we know certain values for theta. One thing I might want to look is like cosine. What value for cosine is that going to be at a maximum? Let's start with 0. So when you have cosine of 0, it's going to be 1 plus cosine of 0. Cosine of 0 is 1, so it's 1 plus 1, or 2. So when my angle theta is 0, I know my r goes out to 2. And so that, and then if you keep plotting more points, so let's do another one. What if I did pi over 2? Well, pi over 2, it's going to be 1 plus cosine of pi over 2, and that is 0, so it's going to be 1. So it's going to come in right here. And if you plotted more points, you would see the shape, and it's not actually going to go out like that. You're going to see a shape kind of going in like this. It's going to dimple in at 1. It's going to do the same thing over here. It's going to bump out, dimple in, come back in, and notice when they dimple in, this will actually go out to infinity. Just like that. So that's roughly your shape if you're graphing it accurately. You can do it better than me. Let's try rose curves. These are interesting as well. So they're called rose curve because you have these petals going on here. And these happen when you have the equations r equals a times sine of n theta, or r equals a times cosine of n theta. So interesting things about this is your n is just a coefficient to the theta, and if the n is even, then the rose has 2n petals. If n is odd, then it just has n petals. So in the case right here, your n is even, so you're going to have, it's 2, and so that's going to be 4 petals, double that. When it's 3 cosine of 3 theta, it's only going to have 3 petals. When it's 4, that's even, so you double it to 8, and when it's 5, that's odd, so it's just 5 petals. Now the neat part of this is, okay, it's figuring out, these petals are going to be kind of symmetric here. They're going to, or spread out evenly, but you got to kind of figure out where these petals actually start. So we just play around with the graph a little bit. Let's try this example. So r equals 3 times cosine through 2 theta. How many petals are going to be? Well, since that's even, you double it, so it's going to be 4. So, and you know those petals are spaced evenly, so I got to find one of them at maximum cosine, and I can figure out the rest. Here's what I mean. Your petals in this case, notice the a value, it's going to go, they're going to max out at the a value. So basically, I need to turn the trig function here, whatever that maxes out at 1, I got to max that out at 1. So these all maximum out at 1. What value for theta in here is going to make that cosine function equal 1? Well, cosine is 1. Do my table right here. Cosine is 1. Cosine of whatever is 1, and that's your x values. That's going to happen at 0 degrees, or 0 radians. So 2 times 0. When your theta is 0, this is going to be 3 times cosine of 2 times 0, so 0. So 3 times 1, which will be just 3. So your maximum happens at 3 out, 1, 2, 3. And I know I have to do 4 petals, right? So I'm going to have my shape, your first petal, and I'm just doing a rough sketch of this. I don't know all those details. That was pretty bad. Let's see if I can do it a little better. So, you know, your first petal is going to look like this. Now, if it's got to be symmetric and I got 4, I know my other petals. I'm going to have another petal going out up to here. And I can prove that when you have theta, pi over 2. Or that wouldn't be a great example. Yes, it would be. No. So I'm going to have one up here. I'm going to have one going out to here. I'm going to have another petal going out to here. So that's going to be my shape. All these are going out 3, and they didn't all go out 3 in my example. This one only went out 2. And they got to be symmetric. So that's roughly what it's going to look like when I want to do the rose shape. Let's do the last one. Lymassans. Oh, man. Oh, boy. Whatever. The graphs of these ones are these two equations right here. So you're looking for the r squared equals a squared sine of 2 theta or a squared cosine of 2 theta. So you're looking for the r squareds. So they kind of form, it's, you know, the figure 8 shapes. So when you have sine of the figure 8, you're going to have an angled sine right here. And when it's cosine, it's going to be straight across. So let's try an example. I want to graph r squared equals 4 cosine of 2 theta. So I got to figure out what my a value is. Since it's a squared right here, my a is going to be 2, because just the square root of that will tell me my a. So I know, and then it's cosine, so I'm going to have this shape. So I know my a goes out 2, so I'm going to go out 2 on my polar, and go out 2 in the other direction. And I'm going to form my figure 8 shape. Just like this. Perfect. So that's how you do this. That's it.